Okay. Well, thank you very much, Lenny. Well, and I would like to thank the organizers because it has been a very nice time here, and also in the last conference in Barcelona. I've been learning a lot about these topics, quantum networks and causal structures and so on. And hopefully next time I will present you something more related to this topic in general. But in the meantime, hope you enjoy this presentation about my flying carpets. Okay, this is about, the title is this one, Free Space Entangled Quantum Carpets. What is it? Okay, first of all, these people is involved in this work. Mariana, Andreas, Perola, Fernando, Steve, and I think that's all. From several places in Brazil and Paris and now in Barcelona. Well, this is about the Talbot effect and how to use it to encode and manipulate quantum information in general. And I will talk about two works. First, again, this one that was published last year, and another one to be submitted soon. So the first part will be related to the previous results. And then, okay, just to make the story as short as possible, this is the message that I would like to transmit you this at this moment. And this is a proposal of an implementation, of an optical implementation of d-dimensional entangled systems. Basically, what I'm going to introduce is another degree of freedom of photons, which can be used to encode qubits. And with this definition, I am going to give you like the recipe to manipulate and measure and all the things you would like to do when you in a quantum information task in general. It has some advantages because the free evolution of the system implements the gates naturally, and you can implement a lot of interesting gates that you would like to do in a d-dimensional system. And it is important because it is a fixed dimension. Who is used to work with photons and experiments knows very well that dimension, for instance, systems with high dimension, let's say orbital angular momentum of light or things like that, the dimension of the system in principle is infinite, so you're working in an undefined Hilbert space in general, and this, let's say you choose, this has the advantage that you are going to choose the dimension of the system. I am going to tell you about what are the scenarios where you can violate Bell inequalities in this d-dimensional system, and what are the values that you can achieve with this system. And also I will try to make to connect these results with other physical systems other than photons. Then, well, this is super basic physics. This is about diffraction, which is very well known in the far field. Let's say when you, these orders of magnitude that you will see once you put a periodic grating in general. I am going to assume that I have this situation, a plane wave here. In general, if it comes with a lot of colors here, so you will split light in this way, and these peaks will be the orders of magnitude corresponding to constructive interference. And this n is the order of magnitude. No? So you approximate in the far field such that you can observe the situation. And this is the condition for constructive interference. But something which is a little bit less known in general in the school and university and physics courses is what happens in the near field. Well, in the very near field, what you observe is if you put a detector here in exactly at the grating, no, you will see exactly the image of the grating, no. So the light passes, and you will see exactly this. But what happens, like in the near region of the grating, is what is called the Talbot effect, and this is what I'm going to show you. So first of all, and from now on, this is going to be valid because we are in the near field. within two approximations. First of all, we are going to consider this is a periodic grating, so in principle it is infinite in the x direction. And also I am going to consider a paraxial approximation, which considers rays which come out of the grating without a divergence in this angle of exit, no? And this is what you see in general in the near field. This is exactly what is called the Talbot effect. The grating is here, no? So at this position, L is the separation between the slits, and you will see, at least if you program, you will see something like this, but it is not difficult to actually see this in the lab, no? And what is going to be important for us are these points, no? Which bright points here that will represent actually a constructive interference, but with a different characteristic than we observe in the far field. So the grating is here, and you can see that physically there appear a different scale of the system, no? In this direction. Of course, you have a scale here, which is the separation between the slits, but as the propagation, you propagate the system, no? The photons, you will observe here that there are specific positions which are relevant, let's say, no? And this is the scale which appears, which is a characteristic scale of the system. And this is actually what is known as the Talbot effect. Well, these bright points here are actually copies or images of what you observe here at the grating. No, these bright points are exactly what I told you in the beginning. No, if I step in at the grating, I will see the light passing through the grating, and after I propagate one distance that from now on I will call Talbot distance, you will observe the same grating, but this time, if you follow this line, you will observe that this is displaced in the x direction. Okay? So actually all these bright points are superpositions of the image of the grating where it was originally with the grating of the displaced in the x direction by half of a period. Okay? I will explain better in the next slide. But this is what happens in general, and then this situation is going to be all these bright points. You can observe here a lot of bright points are nothing but copies of the original grating that was here, but displaced in the x position. Okay, so the interference here, the constructive interference here, is going to be manifested as a creation of images of the grating at the origin. Okay, so what is going to happen is more or less like this. If you are here at the grating, we are going to see like the light in this direction. I forgot to say that in the y direction, I'm not considering diffraction, so this is big enough to forget diffraction effects in this direction. Then if you get apart a little bit here, you will see a grating here and another grating here will appear. This is intensity, no? I'm not just considering the intensity. And then you will see the superposition of these two images. And then if you get apart again, you will see that the grating was displaced. Okay? So this is what you will see as you are falling apart of the grating. And this is what is the Talbot effect again. And well, but this interference pattern is made of something else. No, it's not only the images of the original grating. And what you actually observe if you plot the intensity in different planes, let's say, or lines in the propagation plane. No? Let's say this is the grating and the propagation direction. And if you plot the intensity along these lines, you will observe something like this, which is actually a fractal curve, which is continuous everywhere, but differential anywhere. And this is what is, I mean, Barry and Schleid baptized these intensity patterns as quantum carpets of light. What else? Well, this is actually the part where it comes like the encoding of the information that we are proposing here. And then that's why we call it Talbot carpets. Talbot was 1836, he published these results, and that's why it's the Talbot effect, and then that's why we baptized this as quantum Talbot qubits. Now we are going to consider single photons in this very same diffraction experiment, and then we are going to consider like the state of the grating initially, at the zero position in the propagation as the zero state. Okay. Then the one state, for instance, will be a displaced version of the same grating. Okay. So we have a single photon, which the distribution in the transverse plane is a periodic function like this. Okay. So each periodic function like this is orthogonal to this, and then I have two states that are going to be orthogonal. So somehow the propagation itself is going to do some kind of operation on this basis already, and then we can see or understand this pattern as let's say a computation, if you want to call it, like an application of a gate on this basis. This is our encoding. This is the new, the degree of freedom that we are proposing to do quantum information. And then this is the form. Once you define your basis this way, you could ask what is then the form of the propagation, or what is how it looks, the operator corresponding to the propagation in this basis. And you can see that for a given distance, you're going to have a certain number of copies of replications of your state, and of your original state, or the qubit. Then it's a superposition. And then when you go to the basis that you defined, you can see that for given distances, by fixing the distance, you're going to define the dimension you want to work with. Okay, this is what I wanted to say. And once you define the dimensions you want to work in, you will see that the unitaries that correspond to this propagation distance have this form. This is exactly what I want to say here. Okay, so are actually polynomials in X, where X is defined this way, and in general they have an interesting form for us, that is a circular matrix. These are coefficients which corresponds to the weights that each copy is going to have, and then you obtain this operator, which has certain properties interesting for us. And so this is free evolution, but we are going to do something else. We are going to work a little bit and introduce an easy to implement phase gate, actually, that is actually a phase between the different regions that we are going to define as states. Okay? So with these two ingredients, free evolution and let's say a cheap gate that is easy to implement. For instance, in optics, we can implement it with SLMs. We are going to do a lot of things, and then it is actually easy to see that because we have circular matrices, because of the form of these gates, the natural way of doing, let's say, computation, if you want, with these qubits is by means of the Fourier transform, which is related to the propagation operator and to the phase gates this way. Okay? So if you use phases in the propagation, you can obtain very easily the Fourier transform. Again, in the dimension you want to work with. Okay. So this is an example. Now I have the zero state here. Then I propagate and apply the phases here and here, and here I will have the Fourier transform of the zero state. This is just an example. In general, you can prepare any state of qubits or qubits in general with these two elements, and you are going to do something like this. This is an easy to follow result. You have the zero state, Hadamard rotation along Z. Hadamard and rotation along Z prepares basically any qubit state, and then this is how it looks. Let's say a state preparation of an arbitrary state starting from a zero state. So this is the unperturbed, let's say, Talbot carpet, And then when you introduce phases in the regions that you want in order to create this superposition, let's say, where I have a cosine of theta here plus a sine of theta here, square each one of the amplitudes, okay? This is the, okay, we can also measure these things. I mean, this is a very, let's say, theoretical way of measuring these qubits, which actually demands that each region that corresponds to each one of the states is going to be detected. So, I mean, this is, you can do this in a more clever way in the lab with SLMs and so on, but I mean, you can put beam splitters here for each region, no? And the rest passes, then you can detect, but this is just one way in which you could actually measure these qubits, but certainly is not the best way to do it in the lab. What else? Okay, this is, so I prepare, I manipulate, and I measure my qubits in this way. And, but actually, this was the theoretical proposal, and then the second part is going to, is about how you actually are going to implement this in the lab. In general, there are no infinite gratings, and you don't have plane waves, so you have to invent something else to create these Talbot carpets, or these qubits that we are proposing. And there is, in optics, there is an interesting way of doing this. If you want to encode, for instance, a three-level system, you put a mask which contains three holes, no, three slits, and you put the phases you want to introduce between these levels, let's say, that are going to be transformed in Talbot qubits, no? So you create first the superposition between these three slits, no, images of the slits, and then you put this into something that we call the Talbot synthesizer, which is a set of two lenses and another grating. So what this system is going to perform is something like you have 1, 2, 3, and these three peaks are going to be repeated along the Z direction. Not exactly with the same weight. You are not going to have a perfectly periodic function here, but quite. So this is the way we are going to create in the lab. They are doing this in Rio. Actually, the Talbot qubits, right? Then this is the synthesizer, and then you can think about now two qubits entangled, and we are going to have a laser, a nonlinear crystal, and then we are going to have the two synthesizers here, and then with this we are going to create the entanglement between now these two Talbot carpets. But at this point I would like to stop a little bit because okay, the entanglement here is going to be basically the entanglement that you obtain here from the source, from a nonlinear crystal source, and then you are going to transform this into this basis that I just defined, which is the Talbot basis, and then somehow the entanglement is already there, but we are going to analyze it, let's say, or create it and generate it in a different basis. More or less, that's all. So you can create, you know that because of conservation of momentum, we have correlation between these two photons, no? And then if you analyze in the x direction here and the x2 direction here, you are going to observe something like this for highly correlated photons. A less correlated source of photons in this degree of freedom looks like this. So you will say more or less that this is more entangled than this, okay? So the entanglement that you are going to generate in the Talbot basis is going to be, it is going to depend on the entanglement already present, which is already present in the source here, okay? So then first of all, you are going to start with something like 3, and in this new this is the first step, the original correlations, and then you are going to put the gratings and so on, and then you are going to have, this is the first grating, which creates the superposition of the qubits the way you want, and then the periodicity that you're going to perform in the x direction, which is basically a repetition of this pattern along all the x1 and x2 direction. So this is the entanglement between the two Talbot carpets. Okay? At this stage, I would like to say that this looks like just a discretization of this quantum variable, no? This continuous variable. And yeah, I don't know, it is a question for me now that comes to my mind now. If the entanglement that I'm going to measure here in this discrete basis that I'm defining is actually, let's say, all the characteristics of the continuous variable entanglement is present here. But this is just a question that comes to my mind now. But, okay, this is really like the discretization of the system, and this is how we are going to produce the entangled carpets. Then, this is how it looks, the simulations for how the violation will look when we calculate these Bell inequalities, which depends on the dimension of the system. And yes, if we consider several dimensions and different initial correlations, no? So we start with an initial correlation which is like this or like this, and then we calculate these Bell inequalities as a function of the dimension, and we are going to observe this behavior. This is initially a less correlated state, and the maximally correlated state, which is something like this, no? So this is a violation of a local value of 2, and this is how it works, the Bell violation. So this is the last part, which is the relation to other setups. First of all, I've been working, let's say my talk is all about periodicity in the x direction, but periodic boundary conditions are very similar to rigid wall conditions, no? So actually, if I put two mirrors here, I can put the boundary conditions, which are like rigid walls, let's say, conditions now, and then I can inject light. These are two mirrors, and I inject, this is the mirror and another mirror, and then I put light here, and then I can see something like light repeating the image that we had here, no? So the intensity was here, then passes here, then it goes to a superposition, and several copies in between, and this is like a real experiment that I performed, and then that we noticed that it has a lot of relation with the things that we've been doing. And these people use this more or less like a beam sorter, a boson sampling experiment, because they can inject 1 or 2 photons here, and then basically this also can behave as a beam splitter with several outputs. You insert one of these, and here you have 2 outputs. So this is more or less also a beam splitter. And if you step something here, no, I mean, this is your goal, you can go there and see several outputs here, and you can consider this as a multi-mode beam splitter, multi-output beam splitter. Sorry. Well, this is a relation to other works, and this is also the Talbot effect, the same Talbot effect, but with BCs in optical lattices, and somehow we think, I mean, we think that we can apply all this formalism of Fourier transform and so on in order to manipulate these kind of systems, periodic systems. Also, molecules, this is more or less the same principle. They work with big molecules in diffraction experiment and periodic conditions and so on. So this is also a place where we think we could apply these techniques, and let's say we are providing a way of measuring, basically defining basis for all these kind of systems that so far I think they don't do these kind of things. And again, the takeaway message, I think it is more or less clear that this is, I mean, I started with this, and at the same time these are my conclusions. And thank you again for your attention, and that's all.